Hello, this is section 5.3 for Calc survey, and today we'll be talking about the definite integral as area, which we've kind of already explored this a little bit. So just a quick reminder, if f of x is continuous and positive, so notice in the last two sections we only ever dealt with when the function was above the x-axis. And when I say function, I could be talking about the derivative or just the function. So don't get caught up on this having to be always known as the derivative. So whenever in this notation, that is the function we're finding the area under the curve. Some students will get confused when we call this the derivative, but it doesn't have the tick mark, and I'll get students who get flustered about that. So each term, f of x sub 0 times the change in x. Remember, these are just rectangles we're talking about, and a left hand or right hand Riemann sum represents the area of a rectangle. So that's what we did in the last section. Now, as that change of x approaches 0, meaning the base length of each rectangle is getting smaller and smaller, therefore creating more and more and more rectangles, then the rectangles fit the curve of the graph more exactly, and the sums of their areas get closer and closer to the true area under the curve. So that's where this formula came from, was basically we put that limit notation in front. Limit as n approaches infinity, having as infinitely many rectangles now gives us this very, very immeasurably good approximation of the area under this curve. Okay, so of course that's from A to B. So let's try it. So find the area under this curve between 1 and 4. So here's this sentence written in math notation. So the integral from 1 to 4, and we put our function here, cubed root of x plus 3, and then dx. And if you want to put parentheses around your integrand, that is totally up to you. Right? I figure it's sandwiched in, so I think we're pretty safe knowing that that's what we're finding the area under. All right, so I went ahead and graphed our curve here. That's what it looks like. And then from 1 to 4, that's the area we're finding. And then we just simply typed this into our calculator. Okay, and we'll do that in class. But you are also welcome to explore that on your calculator. There's even some scientific calculators that can do a definite integral. That's what this is called, a definite integral. All right, so area when f of x is positive for some x values and negative for others. So when this happens, so notice here's a picture where part of our area is above the x-axis, but then you actually dip below the x-axis. So the area above is going to be counted as positive. So we count this as positive, and the area below the x-axis is counted as negative. Now, you cannot have a negative area, but we can find this area and we'll stick a negative in front to represent that's where the area was. It's just a notation to note where the area is. Okay, so when you go to calculate this and you put this in your calculator, it spits out a number and it's negative 10.67. Whoa, I can't have a negative area, and I agree with you. So what this is telling me is the majority of the area was below the x-axis, which is true. You can see that over here. Okay. All right. If it asks for the total area of the shaded region, you simply add the areas regardless of it's located under or over the x-axis. All right, so if it would had asked me for the total area, I would have counted both of these as positive. So you would have to break it up. You'd have to do the definite integral from -2 to 1, or -1, sorry, -2 to -1, get that area, and then do the definite integral from -1 to 2 to figure out what this area is so you can turn it positive so you can add the two together. Okay? What I like to tell my students when we talk about this in class is think about those cross-country runners that start at the high school, they go run to the church, and then they run back. So maybe the area above is them running to the church, and the area below is them running back to the school. So if it just said find the area under the curve, which would represent their distance that they ran, it'd be 0. But is that really how far they ran? No. So total area would then take the distance they ran to the church, which is positive, and then it would take the distance they ran back, which is technically negative, but we're going to turn it positive so we can add it together and actually see how far they actually ran. All right. Okay, so decide whether, okay, so this is a definite integral from -2 to 2 of f of x dx. So the area under the curve, from the curve to the x-axis, from -2 to 2, that's what that means. Is it positive, negative, or 0? Well, from -2 to 2, the bulk of the area is under the x-axis, so it's negative. Here, the areas look about to be the same, so this area would be 0. And in this case, now, the reason I put this one on here is when you change it to concave up, I'll have students who will get very flustered because they'll want to tell me this area right here. But it's always from the curve to the x-axis, even when it's concave up. So I know that looks a little weird, but I'll get students who will shade here and then they'll want to shade this region when no, it's always from the curve to the x-axis, and this area is definitely a little bit bigger than this one, so it's positive. All right, the area between two curves. So in this case, if you look at the notation here, so we've got the area between, and g of x is less than f of x from a to b. So we've got f of x that's over g of x. So the idea is, if we find the area under f of x, and that would take it all the way to the x-axis, but then notice they're subtracting away the area under g of x. That would then leave us with the area between the two curves. You did this in geometry. When you had a big circle and there was a smaller circle inside and you had to find the area of the perimeter, you did the area of the big circle minus the area of the small. That's exactly what you're doing here. You're finding the area under the top curve here, the curve farthest away from the x-axis. Find that area first and then subtract the area under the smaller curve, the one closer to the x-axis. And that leaves you with what you want. So you might need to actually graph these to figure out which one is farthest away from the x-axis. Okay, so graphs of f of x and g of x are given here. And so 3x plus x squared, that's the parabola. That's your f of x here. And then 5x to the 1/2, that's here. That's your radical function there. All right, use a definite integral to estimate the area enclosed by the graphs of these two functions. Okay, so again, I just said you have to figure out which function is the farthest away from the x-axis. And so if you look, start at the x-axis, the first one you hit's the closest, and then it's actually g of x. That's the farthest away. So that's the one you'll want to put first. So the integral from, and use your calculator to find that intersection point. So the integral from 0 to 1.33, notice it's the function farthest away, 5x to the 1/2, minus the function that's closer, dx. So it'll switch, don't get caught up on, and it's always f of x minus g of x. No, that's not true. You need to graph it to figure out which one is farther away. Okay? And if you get a negative answer, that's a good indicator something's probably not right. Okay. All right, so make sure I don't miss anything. So just make sure you're doing your homework. It's starting to get a little fun with the new notation, not having to do rectangles anymore. Make sure you're practicing with your graphing calculator, and you want to get really comfortable and familiar with this new notation and what it means. Okay, so just make sure you're doing your homework and email me if you have any questions.